So our next speaker is Samara Renn. Samara studied mathematics and computer science in the US, I think in Illinois. And then you joined the group of Mark Pauli at EPFL. Did your PhD there. So I guess therefore your research interests are physical modeling, digital fabrication, things like that. Optimization, numerical optimization is probably always involved. And you now, or very recently, joined IST Austria. So I think this is good because now we can collaborate very efficiently. We are very much looking forward to your presentation with the title Computational Inverse Design of Shape-Morphing Structures. Please.
Thank you so much for the introduction. I'm very happy to be here. I'm very honored to be invited to this event. And today I want to present my work on inverse design of shape-morphing structures. Shape-morphing structures are structures that can transform among multiple geometric configurations. Here we see two examples. On the left is a heart stent that starts from a compact state to enter the blood vessel and then expand to prevent the vessel from closing. And on the right, we see an origami-inspired solar array that can be transported in a compact state and then fully expand to maximize sunlight exposure. And we actually saw a similar structure in the talk of the previous speaker as well. Shape-morphing structures not only have applications as medical devices and space technology, but also in soft robotics and lightweight architecture and many others. There are several interesting and powerful qualities of shape-morphing structures that are crucial for these practical applications. The first one is shape approximation. Shape encodes many important functionalities and information in engineering and design applications. For example, for customizable medical devices, we want structures that can conform to the patient's body and adapt to their movements and changes. Another feature that we're interested in is deployability. Deployable structures can transform into different states automatically or under simple iterations, which make them efficient to fabricate and transport. The structure on the top right here is also exhibiting bistability. After deployments, bistable structures can maintain their final configuration without any external forces present, which make them more economical to maintain and more robust against changes in the external conditions. Creating these shape-morphing structures that balance all of the different design goals ultimately involves solving a challenging set of inverse design problems. We want to design structures that has an easy-to-fabricate compact state and can be robustly and accurately transformed into a complex target state. The design process will then start from the target states, and we want to find and optimize the parameters of the fabrication states. This is what we call an inverse design problem. We generally have a lot of freedom in choosing the fabrication state. Thanks to digital fabrication technologies such as 3D printers and laser cutters, even very complex geometric shapes can be considered as simple to fabricate. And the challenge really lies in what is the fabrication state that we want? How do we compute the optimal fabrication parameters so that the structure already encodes the transformation process and the target state? Unfortunately, this is a very hard problem to solve. To see some of its complexities, we first know that we usually have tens of thousands of design parameters, which means the traditional design process that involves trial and error is infeasible. The transformation process will often involve integral and differential equations. They can range from either simple kinematic foldings or complex chemical reactions. And these equations are often high-dimensional and highly nonlinear. The design target could then involve conflicting goals that add global coupling to the system. For example, for many architecture applications, we want structures that are both strong but also lightweight. On top of all these, we want to find the inverse of this process, so we can find the optimal design parameters to achieve these target goals. In order to address these challenges, we work on developing good geometry abstractions and efficient numerical method. Today, I want to present two examples of shape-morphing structures that we have studied and designed. Having a computational framework not only allows us to analyze and design improved existing structures, but also enable the creation of new morphing structures with previously unachieved properties. A strategy that we have found to be particularly useful in designing these structures is to first examine the simplest possible units of the material system, and then apply the insights we gain from the unit cell analysis in the design and optimization of the entire structure. So I'll begin with the project on 3D weaving with curved ribbons. This work is inspired by the art of basket weaving, and I want to demonstrate how computation can be used to enhance this ancient art. The history of weaving goes back thousands of years. Traditionally, people use natural materials such as bamboo. After harvesting the bamboo pole, we can use a simple tool to split the bamboo into straight ribbons and then interleave them to build a woven patch. People have applied the technique of basket weaving in many domains, including architecture, medical devices, and fashion design. Existing weaving techniques mainly relies on straight ribbons, and the shape in these applications are relatively simple. I want to argue that the design space of 3D weaving is much larger than just straight ribbons, and by expanding the design space, we can build woven structures that can approximate more complex shapes. For example, by using a laser cutter, we can easily fabricate this set of planar curved ribbons shown on the right. And if we weave these ribbons, we'll get this woven bird. We see that even from this very sparse set of ribbons, we are already able to approximate many features of this bird very well. The fabrication process of these curved ribbons is more or less the same. Well, it's very straightforward thanks to the laser cutters, and the weaving process is very similar as well. The main challenge really lies in the design of the ribbon shape. How can we find the curvature of the ribbons and the spacing between them so that when we assemble them together, they will approximate this input target shape of a bird? To begin, I want to first demonstrate why the in-plane curvature parameter is such an important and effective design parameter for controlling the shape of woven structures. The geometric principle of weaving can be nicely explained by the Gauss-Bonnet theorem. To understand how to apply this equation for 3D weaving, we'll focus on the unit cell in this pattern. The variable m in the equation is the surface domain. In our case, the boundary of m is this hexagon. And the first term in the equation is the integral of the Gaussian curvature over the surface domain. The Gaussian curvature is an intrinsic property of the surface. In order to achieve the shape approximation goal that we discussed earlier, we want to control the integrated Gaussian curvature for each cell in the weaving pattern. And we'll do this by using the second term, which is the integrated geodesic curvature. In our case, the boundary of the domain is made of 6 piecewise smooth curves. So we can separate this integral along the boundary into the integrated geodesic curvature along each curve and the sum of all turning angles between these curves. In particular, since we're currently looking at the unit patch with straight ribbons, the geodesic curvatures are 0. And the turning angles of a planar polygon will sum to 2 pi, which cancel out with the right-hand side, which leaves that the integrated Gaussian curvature is 0, and that matches with what we began with, a planar weave. But now that we understand this relationship between Gaussian curvature and geodesic curvature and turning angles, we can start to get more interesting patterns. If we start with the regular weaving pattern again and cut one side of the hexagon out, stitch the two new boundaries together, the center hexagon will be replaced with a pentagon. We have reduced the sum of turning angles by pi over 3, and hence the structure now becomes positively curved. We call the pentagon here a topological singularity because it has interrupted the regular grid of hexagons and causes the ribbons to change directions around it. Similarly, we can insert a new section instead and hence increase the turning angle by pi over 3. We'll then get a negatively curved surface. Introducing these kind of topological singularities has been widely used in basket weaving design. For example, we see singularities at the corner of the basket shown here. The second and often neglected method to introduce curvature is to adjust the integrated geodesic curvature, or in other words, to use curved ribbons. If we take the hexagon module again and decrease the geodesic curvature of each ribbon, the patch will have positive curvature. If instead we increase the geodesic curvature, we'll get negatively curved patch. Compared with inserting topological singularities, where we go from polygon to polygon discretely, we can continuously change the curvature of the ribbon in plane, which will in turn changes the 3D curvature continuously. Here we see the left torus is woven with straight ribbons and singularities, which causes sharp corners in the shape. And on the right, we have a structure that's woven with optimized curved ribbons. It has a completely regular topology with no singularities and approximate the smooth mathematical torus closely. Our geometric analysis shows that the planar curvature parameter of the ribbons are very powerful. By using curved ribbons, we greatly increase the design space of the woven structures and were able to create many previously impossible woven geometries. Here is a preview of some of the woven structure that we have designed. The geometric abstraction only gives us half the answer. In this project, we not only want to build woven structure that approximate the shape of the geometry of the target shape, but also want it to settle reliably back into the predicted shape, even after some extreme deformations. And for this, we need to consider the complex interplay between the elastic behaviors of the ribbons and the contact forces between them. We model the ribbons as discrete elastic rods. Using this model, we can efficiently compute the bending, twisting, and stretching energy of the ribbons. In addition to understanding the elastic energy stored in the ribbon, the over-under interleaving pattern and the contact forces between these ribbons are also crucial for the equilibrium states of woven structures. In our framework, we defined a set of equality constraints on the elastic rods variables to ensure that the ribbons follow the over-under patterns and lie flat on top of each other to promote stability in the structure. We implemented these constraints efficiently through nonlinear changer variables so that in the end we solve an unconstrained optimization problem. In order to construct such an assembly of discrete elastic rods, we take an embedded graph as the input weaving pattern. The user can either directly provide a weaving pattern or specify any surface mesh, and we can compute its medial dual graph as well as the alternating over-under patterns of the ribbons to use it as the weaving pattern. Our algorithm will automatically pair up edges to trace out ribbons and initialize them to be straight. We can then try to find the equilibrium states of the initialized structure by minimizing the total elastic energy stored in all the ribbons. Unfortunately, we see that this first structure is not ideal. In particular, the ribbons have lots of twisting and buckling, and the crossings experiences high stresses. This is because currently, this topology has no singularity. It's completely regular. All of the ribbons are completely straight, so it really cannot conform to the target 3D curvature. We will now improve this structure by numerically optimizing over curved ribbons. As we have learned from our geometric analysis earlier, the effective optimization parameters are the length and curvature of our ribbons. In order to compute the optimal parameters, we'll solve a multi-objective optimization problem. Our first objective term here tries to approximate the target surface as closely as possible. Under this term, the ribbons are allowed to slide on the target surface, but not away from it. The second term tries to search for woven structures with low elastic energy so that the material experiences low stresses. Previously, when we evaluate the elastic energy, we assumed the length and curvature ribbons are fixed. But now in the design process, the equilibrium states x star will be a function of these design parameters. Once we know how to compute the elastic energy, we can evaluate the forces at the crossings as the gradients of the elastic energy. In order to have a stable weave, we need to have these forces be compensated by static frictions and compressive forces between the ribbons. Lastly, when solving the best design parameters, we need to constrain the structure to be in equilibrium so that the surface deviations, stresses, and forces between the ribbons that we evaluate for the objectives are actually physically meaningful. This nested optimization problem is very challenging to solve. We typically need to use high-resolution center lines in the elastic rods model to accurately simulate curved ribbons. For example, we have over 100,000 variables for the woven client model. But what's worse is that we cannot simply apply a standard numerical solver for this problem because the objective function already depends on the solution of an equilibrium problem, which is a highly nonlinear optimization problem on its own. In order to get the derivative of the equilibrium solution over the design parameters, we perform exact first and second order sensitivity analysis using the adjoint states method. The schematic illustration here shows that as we update the design parameters follow the direction given by the sensitivity analysis, we have now deviated from equilibrium states. We need to resolve the equilibrium problem with respect to these new design parameters to go back to the elastic equilibrium manifold. And we need to perform this projection after each iteration of the design parameter updates. In order to speed up the convergence of the equilibrium problem, we can get a good initial guess for the next equilibrium states using quadratic Taylor expansion of the previous states. So the updates actually follow a quadratic approximation of the manifolds, and the equilibrium will converge rapidly. Here is a recording of the optimization process. The color here indicates the distance from the woven structure to the target shape, and we see that the distance is decreasing as the ribbon going from straight to curved. Once we have found these optimal curvature parameters, we can fabricate these ribbons easily using laser cutting. To facilitate the weaving process, we engraved the crossing numbers on the physical ribbons. And we also have a visualization app where the user can interact with the woven model. We can then weave the ribbons to get the final woven model. In order to validate our inverse design method, we scan and reconstruct all of the physical models that we built to compare them with the input target surface. To also demonstrate that using curved ribbons allow us to continuously control the woven shape, we created an example where we morphed the sphere into a cat without changing the topology of the weave. We only used the curvature parameter to achieve this shape change. In the weaving project, the unit cell analysis was purely geometric. For the second material system that I'll discuss, we'll see that geometric analysis is not sufficient, and we quickly need to apply physics-based simulation even at the unit cell level. This project is about surface-based inflatables. I'll first introduce the material system and then explain our physics-based unit cell analysis and how that allows us to create a wide variety of inflatable structures. Surface-based inflatables are constructed by taking two sheets of materials, fuse them at a set of curves, and optionally cutting away certain regions. When inflated, the unfused region will separate to maximize the enclosed volume. These structures are characterized by the fact that the inflated thickness is small relative to the overall structure, so they can be considered as a thin shell. Compared with curved-based inflatables and volumetric inflatables, a surface-based inflatable can approximate non-watertight surfaces because only the shell itself is pressurized and the volume enclosed by the shell is not pressurized. This feature makes it straightforward to turn surface-based inflatables into practical functional objects such as a medical neck brace or an architecture rooftop. In order to understand the deformation behavior of surface-based inflatables, we'll start with a very simple fusing pattern. If the fusing curves are all straight, when inflated, the sheet's material will contract horizontally, but the length remains unchanged in the other direction and the structure remains planar. If instead we have concentric circle fusing curves, when inflated, the sheets will contract radially, but the circle circumference remains unchanged, which will wrinkle up and force it into a saddle shape. Parallel fusing curves are nice because we can easily understand their deformation behavior just from the geometry. Unfortunately, parallel tubes suffer from near zero bending stiffness around the tube direction. which can lead to a catastrophic loss of structure stability, as we've seen here. Luckily, the design space of surface-based inflatables is much larger than just parallel tubes. Experiments have shown that by just using a zigzag pattern, we can already get much better stiffness behavior. This is our main motivation to develop a framework that can analyze arbitrary fusing patterns and employ them in an inverse design framework. Our goal is to create inflatable structures that can approximate a wide range of shapes, but also maintain structure stability. The central question for our design framework is, given the fusing curve pattern, how do we find its weakest bending deformation and the corresponding stiffness? Compared with standard material testing, where we apply some simple stretching or bending and then see the response of the material, here we want to understand, under the inflation forces, how does the material respond? For parallel tubes, the fusing lines essentially function as free hinges that exert zero resistance to bending. For more complex patterns, such as this one with the elliptic holes, it's unclear how we can directly infer the bending behaviors from the geometry, and instead we need to turn to physics-based simulation. The general idea that we'll use to analyze a fusing pattern is to consider a homogeneous material built from an infinite tessellation of this pattern, because then we can apply standard theorems from continuum mechanics to analyze the stretching and bending stiffness of this new metamaterial. In order to make this idea of infinite tessellation computationally trackable, we apply homogenization theory by defining a simulation problem with periodic boundary conditions. The simulation objective here trying to balance the elastic energy stored in the sheets and the work done by the pressure potential. The periodic boundary conditions specifies that the unit cell needs to have matching deformations on opposite edges. In order to implement this tessellation condition properly and efficiently, we want to directly characterize all the admissible deformation permitted by the periodic boundary condition. And to do that, we'll reparameterize the deformation of the unit cell using 4 variables. The first variable, S bar, is a symmetry matrix that parameterizes the average in-plane stretching. Then we have kappa bar and alpha bar together parameterizing the bending behavior of the unit cell, where kappa bar specified the curvature of the bending and alpha bar specified the bending axis. Lastly, we have the vector U, which specifies the fluctuation displacement, which allow the sheets to relax into equilibrium states that's consistent with the average stretching and bending. With this parameterization, we can transform the periodic boundary condition into just equality constraints defined on the fluctuation variables only, and we can again implement this efficiently through change of variables so that we solve an unconstrained optimization problem in the end. Once we implemented this simulation problem, we can now analyze contraction behavior of unit cells with arbitrary fusing curves. The cell on the right has an outer plane equilibrium state, which means that here it has already chosen, the equation here was trying to show that with our parameterization, we can also easily evaluate the contraction factors of the unit cell by just solving an eigenvalue problem. This unit cell here already has an outer plane equilibrium state, which means that it has already chosen a preferred axis of bending, and it will now strongly resist bending around any other axis. So the analysis here is complete. Unfortunately, for the remaining patterns, their equilibrium states remain planar, so we still need to do more analysis to find out what are the strong and weak bending axes. Sadly, here we cannot infer the weakest bending direction similarly to how we did for stretching by just using an eigenanalysis, because the planar equilibrium states corresponding to a singularity of our bending parameterization. And this cone singularity here is inherent to the space of single-axis bending that cannot be avoided through just reparameterization. Despite the difficulties caused by this singularity, we were able to derive a compact analytical formula for the bending stiffness of any unit cell. We proved the equation here that says the small strain single-axis bending stiffness profile of any unit cell with the planar equilibrium states is simply a linear combination of 5 basis functions defined as powers of cosines and sines. The cost for computing the coefficients of the basis functions, and hence the entire bending stiffness profile, is equivalent to one iteration of the simulation problem, thanks to our parameterization. Here are the bending stiffness profile computed for the unit cells that we have seen before. The analysis on the parallel tubes matches our intuition. This radial plot here is showing along the horizontal direction, the bending stiffness is 0 because the free hinges of the fusing curves, and at 90 degrees, the bending stiffness reaches maximum. In practice, we want to choose unit cells whose minimal bending stiffness is above a certain threshold, so we can use it to build strong structures. The rightmost pattern is interesting because it has a threefold rotational symmetry and a completely isotropic bending stiffness profile. Unfortunately, the magnitude is very small, which means that the pattern is very weak and not suitable for creating stable structures. To use the remaining patterns in our inverse design optimization, we first need to parameterize them to create families of unit cells whose material property varies smoothly over their pattern parameters. For example, we can parameterize the cosine curve pattern using its amplitude. The parallel tube pattern can now be considered as a special case where the amplitude is 0. As the amplitudes increase, we see that the stiffness profile becomes more and more isotropic until it switches to have strong bending stiffness along the horizontal direction. We can similarly parameterize other patterns using their geometric features and then sample parameters along each dimension to create a database of fusing curve families. Here's the visualization of the contraction factors and bending stiffness properties of the three pattern families that we have seen before. Again, the parallel tube have an extremely anisotropic contraction behavior and bending stiffness. But now we also have data on a much larger set of patterns, and we can employ this material property database in the inverse design optimization. Given a target surface, and also in this case a fusing curve family, we want to find a flattening of the target surface so we can fabricate a planar structure that inflates into this target shape. Finding a flattening function is a classical problem in computer graphics. For example, it occurs when we need to create a planar map of the Earth. In the case of designing inflatables, in addition to just finding the flattened domain and correspondences with the target shape, we also need to find the fusing pattern. We can think of it as for each point, we can choose from a stack of textures. In this case, just cosine curves with different amplitudes. And the problem is which one is the best one. When we place a unit cell in the flattened domain, we need to define the orientation of the unit cell in addition to the pattern parameters. And we'll find the optimal parameters again by solving a multi-objective optimization problem. The first term here tries to align the first term here says that the distortion caused by the flattening should be compensated by the contraction behavior of the unit cell, so that when inflated, the structure can approximate the target shape's metric. We also have a second term that tries to minimize the approximated bending energy of the overall shell. Intuitively, it's trying to avoid aligning the strong bending axis of the unit cell with high normal curvature of the target surface. Because if you try to do that, the cell, when inflated, will want to stay planar instead of approximating that normal curvature. Once we solve this nonlinear parameterization problem and find the optimal unit cell parameters, we can then compute the fusing curve at a user-defined frequency and mesh the domain to run the inflation simulation. If the inflated states deviates from the target shape, we can then run a full-scale optimization directly optimizing over the fusing curve parameters. This numerical problem is similar to the nested optimization that we saw in the weaving project. For this particular target surface, the results after the unit cell optimization is actually already quite good. But we see that for this other example with elliptic holes, the nested optimization can further improve the shape approximation quality of the inflated structure. We fabricated our physical prototypes using an infrared laser mounted on a CNC bed. It takes about 20 to 40 minutes to fabricate a model, depending on its complexity. Here we see inflation videos of two structures that has the same target shape, but we used different fusing patterns. The left one has the parallel 2 pattern, and the right one has the cosine curve pattern, and we see that the cosine curve model approximates the target shape much better. We also have other prototypes using the dashed line pattern. For this project, in the end, we fabricated 6 prototypes using 3 different types of patterns, and we again scanned all of these physical models to compare with the target shape to validate the shape approximation objective. But additionally, we also want to validate that different fusing patterns will produce different structural behaviors. We conducted a series of load tests to measure the deviation of the structure from its target states. And we see that in both cases, the structure optimized with the cosine curve pattern performs better. For both of these material systems, we're able to leverage computational methods to transfer the complexity in assembly, actuation, 3D shape approximation, and structure stability into the geometry of the fabrication state. I have mentioned many potential applications, and we have conducted many design studies, but of course, there is still a lot to be done to bring the current state of research into actual products. For example, to use these shape-morphing structures in large-scale architecture applications, we need to carefully consider their assembly sequence or actuation sequence. Surface-based inflatables also enable many potential medical applications. The model here is designed to be a medical neck brace. The idea is that we could scan a patient's body and then design an inflatable that approximates the patient's shape as closely as possible to provide the best supports. But beyond shape approximation, there are many other properties that we should consider in the design process, such as pressure and temperature control and sensing capabilities. Another very interesting future direction is to think about actuations of this inflatable structure. Theoretically, to fully capture the dynamics of these structures, we need to run a fluid simulation to track how air propagates in these channels. But this will be very expensive. It still probably is a very interesting research problem. But one idea to get around this problem is maybe we could segment the structure into multiple individual chambers that we can control, so we can more directly modulate the inflation process of the structure. And related to the idea of multi-chamber inflatables, we can also fabricate them by just stacking and fusing more than 2 sheets of material. In this example here, we can take 3 sheets to create a top chamber with the concentric circle pattern and the bottom chamber with the spiral fusing lines. If we actuate and pressurize both chambers, we see both these patterns appearing and the inflated shape settle into something in between. But then we can dynamically control the pressure value in each chamber and actuate the structure to go into a saddle shape and then a cone shape. It will be very exciting to turn multi-chamber surface-based inflatables into robots and integrate our design algorithm in a robot design framework where we can understand the how do these actuated shapes interact with the environment and what kind of local motion they could induce. To conclude this presentation, I want to present an application that we were already able to achieve. BAMX is a pavilion-scale woven bamboo structure built with deployable units. We applied our computational framework to optimize the locations of the crossings of the bamboos and reduce stress concentration in the material. We adopted a top-to-bottom assembly strategy so that the weaving can be done on the floor level. The entire structure weighs less than 150 kilograms and spans 10 meters in diameter and 4 meters in height. One of the lessons that we learned from building a larger structure like this is that modularization is crucial. In this structure, all the cylindrical parts can be fabricated off-site and stored compactly because it's deployable. And then on-site, the main task is to weave these units together, weave these cylinders together. This structure has been exhibited outdoor for over a year now with plants growing over it, sort of like nature reclaimed the material. And I hope that in the future we'll have many more opportunities to apply our research results in real-world applications. I want to thank all my collaborators for their valuable contributions to these projects and our funding agencies for supporting our research. And thank you so much for listening.
Thank you very much for this very interesting presentation, and if I may add, very beautiful presentation.
Thank you.
Are there any questions?
You mentioned this problem of, very nice actually. So you mentioned this idea of having multi-chamber. I mean, is this also targeted a problem that if you start blowing air into one side, it's very hard for the air to actually reach through all of these channels to the other side, because having kids and having some of these, if you have like inflatable mats and so on, some of these are designed in a way that it's actually, if you try to do that, it's actually very hard. Also to get the air out of it. I mean, getting the air inside is one thing, and that usually works, you just apply pressure. But getting the air out is even harder, because then it contracts somewhere, and then it blocks the air, and then you don't get the air out again, except by cutting somewhere or being very careful about it.
Yes. Yeah, and this is also one of our motivations to analyze these more complex patterns, because in the beginning we have the parallel tube pattern, then when we design with them we get these long individual chambers. But if, say, we use a fusing curve pattern with elliptic holes where the fusing curves are disconnected, which means that the inflation chamber is by design just a single chamber and the air can flow through much more easily. Of course, we still need to do more analysis to find out exactly how these fusing patterns affect air flows and so on, but that's one of the motivations to analyze patterns beyond parallel tubes.
Are there further questions? So, yeah.
Yeah, thank you for this lovely presentation. This is Simon from the Institute for Building Construction from the University of Stuttgart. And we, every once in a while, offer seminars where we build pneumatic structures with our students. And so it was really great for me to see your shapes, which our students came up with the ideas 2 years ago. And we have great difficulties, I have to admit, to create airtight structures in a large scale. And so maybe you have a hint how you do it. We have an ultrasonic welding machine by Pfaff, and it's still tricky to get it airtight. And, I've seen the answer for how to get the air out. I've just seen recently a sculpture in Hamburg by an artist company, and they've inserted large airtight zippers to get the air back out. That was really clever, because we've had the same issue. How do we get the air out? We have little holes where we pump the air in, and
so you mean like the fusing curves will in fact be zippers? We can just actually separate the two sheets. Yeah.
So
that's great.
If you have any hints how to get airtight, large structures with students, I'd be happy.
I mean, I can talk a little bit about more about our construction. The material we use is woven nylon coated with TPU, so a plastic layer. And then the process is like the image I showed with the laser is the laser will melt the plastic parts and cause the fusing. And to sort of combat the issue that to prevent them from separating easily, we actually also have this special dye that we deposit along the fusing curve to help with the laser absorption. And additionally, we need this minimal width of the fusing curve. Like some of these models that we built, for example, the neck brace currently is larger than a human neck size because our fabrication methods right now need the fusing curve to be 2 millimeter, so we cannot reduce the size of the model further. So definitely, I agree, this is still challenging. I think either scaling up or scaling down on actually fabricating them. But yeah, I would love to talk more to explore more later.
Thank you very much. In the interest of time, we should carry on with the next presentation, and I will hand over, and let's thank Samara again.